Welcome to the online causal inference seminar. Today we're excited to have Mark van der Laan from UC Berkeley, who will speak about higher order targeted maximum likelihood estimation. In Q&A, there's a collaborator of Mark, Zhe Wang, who will try to answer all your questions. Mark van der Laan will also take a break in the middle of the presentation to answer your questions, so please submit them via Q&A. After that, we have a discussion by Alex Luedtke from the University of Washington. Today, questions will be handled by Guillaume, so I'm switching over to him now.
Thank you, Dominic. So as Dominic said, Zhe Wang will handle the Q&A. So please submit your questions there. We'll select a few of them that we'll ask Mark live. If your question is selected, I will ask you to raise your hand and I will unmute you. Please do not raise your hand until I've asked you to do so. All right, thank you very much. And Mark, feel free to start whenever you are ready.
Okay. All right. How is this looking?
Good.
All right, good. Yeah, thank you so much for the invitation and the opportunity. So today's talk will be about higher order targeted maximum likelihood estimation. Target maximum likelihood estimation is a general approach for statistical estimation in highly non-parametric and flexible models. And what I talk about today is an advance within that framework. How to go to the next slide. There we go. So here's an overview. I will first review the regular TMLE, which I now call then first order TMLE, an important machine learning algorithm, which is called highly adaptive lasso, which also will be an important ingredient for the higher order TMLE, which is just an MLE over a big function class. I then focus on defining the second order TMLE. I demonstrate why that it optimizes an exact remainder of the first order TMLE and thereby makes it a third order remainder. I present an exact expansion for the second order TMLE, which also allows us for higher order inference and understanding. I show the generalization to k order TMLE so that you actually work with a k+1 order remainder. And we'll show simulations for the average treatment effect and also another example, which is more theoretical interest and has been studied accordingly, which is the integral of the density squared. And then we end with some concluding remarks. First, I need to bring this back into what statistical learning is about. Now, the first step is, of course, that the observed data we are seeing, we often, let's say, denote it with like O1, O2 up to ON. So we have N units and we observe records on them. And that data is a random variable. It's the result of an experiment. And therefore, it also has a probability distribution. We often call it P0 or P0N to indicate if it's the distribution of the whole overall data. Then we need to agree on what do we know about the likelihood of the data, what do we know about the probability density of the data. That's called a statistical model. And we want to do that in a realistic way so that the true data distribution is still included, so satisfies these assumptions. We then need to define and query about our data distribution, and we call that mapping psi. So psi maps the true P0 into a number, and that often comes from the whole causal modeling, defining a causal quantity, establishing identification, so that you then have an estimate. So that's where causal inference comes in as a way to define an estimate of interest which approximates the desired causal effect the best you can under transparent assumptions. But this talk is really about the estimation once you have reached that state. Then we need to define an estimator, and that's what this will be all about. And then, of course, for confidence intervals, we need to understand the theory of the estimator. We need to understand the sampling distribution of the estimator so that it has, let's say, approximately normal distribution, and so we can construct confidence intervals. Now, targeted learning is defined as the subfield of statistics, which is concerned with the development of estimators of the data distribution. I call them PN star, which come then with a plugin estimator psi of p n star, and we want these plugin estimators to have good behavior, so that we want them to behave to be consistent, asymptotically normal, and also provide confidence intervals. And all this needs to happen in realistic statistical models, which will be infinite dimensional and highly non-parametric. So by necessity, to learn the stochastic relations between the different variables you observe, you need machine learning, and therefore machine learning will be an intrinsic component of this, but we also need to make sure we are getting formal inference. And so that's where we get the bridge from machine learning to statistical inference. In this talk, I will focus on the case where we observe n IID independent identically distributed copies of a random variable. So that is all about this common probability distribution and a feature of it. But there's lots of work we also have of things like time series, networks, and adaptive designs, which are really sample size one problems. So TMLE is completely applicable to that. Okay, so what is the first order TMLE? So what you have now, you have this parameter psi, which, like for example, we'll do an example like an average Freeman effect. And we have to study that parameter as a mapping from the probability distribution, like the density of your data to the real line. And in particular, we have to calculate the so-called pathwise derivative of that. And that defines then the so-called canonical gradient. So you take paths through P, little parametric models. We call them P epsilon. You have psi of P epsilon. You take the dd epsilon, the derivative, and write it as a covariance of some function with the score of the path. And that function is called the gradient. And in particular, we can choose it to be the canonical gradient. Now, that canonical gradient is a very important object because it defines a path. If we compute a path like P epsilon with score that canonical gradient, that path is all now about, has a fluctuation parameter, and that path is all about changing the target parameter maximally for every small change of epsilon. And so that one will be used to do the TMLE update. And so the procedure then starts with, first, we need an initial estimator of the data distribution P0. So here you can use your, like we often propose super learning as a way to build a library of many algorithms, and that cross-validation decide which algorithm performs best. But there are other, you can choose whatever you want, as long as it has to be flexible, it has to be a good estimator of the data distribution P0. Then we take this least favorable path, as we call it. So it's this path which has a parameter epsilon, and epsilon 0, you get back your initial estimator, and it has score the canonical gradient. And what that means is that your psi along this path, when you move epsilon from 0 away, will have a maximal square change for every essentially unit increase in epsilon. And therefore, when you do an MLE along this path, it's like fitting the parameter. And therefore, you get a lot of gain from that little single MLE step. You get a big bias reduction for your target parameter. And that's what gives us the bridge from a machine learning estimator, which will not provide inference, to suddenly this target estimator for which we will have inference and all that. So it's a simple MLE. As I say here, the epsilon n1 is just the maximum likelihood estimator. L is the log likelihood loss function. It can be generalized to other loss functions, but let's talk about log likelihood. And then you take your update. So you now say, okay, that along that path, I moved my initial estimator to an update with that MLE, and that becomes my targeted maximum likelihood estimator of the density, which is now tailored for the target estimate. And so we plug it into our psi mapping, and we get our psi pn1 star, and that is then the targeted maximum likelihood estimator of the estimate psi 0. This estimator solves in particular the efficient impulse curve equation, in order to the score being the canonical gradient, and you set empirical mean of that equal to 0. And that's an important ingredient, and that really drives the theory of this estimator. And so the theory of this estimator can be summarized in one page. Firstly, what you do, you define what we call the exact remainder. In this, I call it R1, because we also have one later R2 from it because of the second order TMLE. And it's nothing else than doing a Taylor expansion, a first order Taylor expansion at P. So you take psi P minus psi P0 minus this linear mapping in P minus P0, which can be written as an expectation operator P minus P0 applied to the canonical gradient. And so this remainder will always be a second order term, will show that for example, for the treatment-specific mean and other examples. So it will be like an integral of something like p minus p0 squared, that kind of thing. And so this remainder tells us in particular that I can apply it now to p being the TMLE. So I get now that the psi of the TMLE, the psi of Pn1 star minus psi P0 equals the minus P0 applied to the canonical gradient at the TMLE plus this exact remainder, where I use that the P of the canonical gradient. The canonical gradient has mean 0 under P. And then we combine that with the score equation, because the empirical mean of the canonical gradient equals 0 because of being a TMLE. So now you add that on, and you get now this key equation for the TMLE, which is really in every paper we write, this is the start of the TMLE analysis, and essentially you're done by then. So you say that the psi of Pn1 star, the plug-in estimator, minus psi P0 is the empirical process, Pn minus P0 applied to the canonical gradient at the TMLE, plus this second order remainder. So now, if you can show that the second order remainder is small op n to the minus half, so it goes away even when you blow it up with square root sample size, then you're essentially done, right? Because then all you need is that Pn minus P0 applied to the canonical gradient. You want that canonical gradient not at the random Pn star, but you want it at the P0. So you need a little bit of consistency in a so-called Donsker-Glass condition. But even that could be avoided with so-called cross-validated TMLE. But either way, that's not really a key ingredient and key assumption. And so you push it then immediately towards the statement that the TMLE minus the estimate equals an empirical mean of mean 0 independent, identically distant random variables plus something negligible, some op n to the minus half. And so therefore it goes to a normal distribution with mean 0 and variance, the variance of this canonical gradient, which is also called the efficient influence curve. And this is by definition means that the estimator is asymptotically efficient, so that among all regular asymptotic linear estimator, it's an optimal estimator. So what you see from this, it's all about the second order remainder being small. And that's exactly, where the key is. That's why you want a good initial estimator in particular. Now, inference follows. You can, because once your estimator behaves like a sample mean, you can calculate on wall type columns interval. You compute the sample variance of your influence curve, which is this canonical gradient, and you get your natural confidence interval for free. So that's not any extra work. Okay, so a running example is that we have NIID observations on every subject. Let's say we have some baseline history W, which is a bunch of covariates. We have then a binary treatment assigned to the subject, maybe in an observational way, and then we collect an outcome and make it, for now, a binary outcome Y, which is like the person died or not. And we then define as target estimate this psi of P, which is you take the conditional probability of death given treatment and covariate, and you set treatment as 1, and then you take the average over your covariate distribution. You could do the same for treatment being control, A is 0, subtract it, and you get the so-called average treatment effect. In other words, that will actually equal the average treatment effect under the assumption of no unmeasured confounder. So this is the estimate, which is often targeted in causal inference. So now we can analyze this psi of P, and we can calculate the so-called canonical gradient, and that's nothing else than a score. And it will have a score component for each factor of the likelihood. Here you see the dp1, which is this canonical gradient. The first component is a score for the distribution of y given a and w. The second is just a function of w. That one will be normally used to target the distribution of w, but since we estimate just the distribution of w of the empirical distribution, that one doesn't have to be targeted, so that's can be ignored. And it's all about that first component, which is this y residual times a over the probability a given w, and that is the important component of this canonical gradient, and also will define the TMLE-step. The exact remainder can be calculated here, and that is indeed second order, and it's given by this integral of the outcome regression minus the true outcome regression times the propensity score minus the true propensity score divided by the propensity score. So it's this, it's a kind of a nice term with a cross structure. And we often think of this as, so we call this a double robust estimation problem, because this remainder will be 0 if one of them is correct. The canonical gradient tells us how to do the TMLE, because this tells us, oh, we need to come up with a path through the outcome regression, which has a score this component. Now you do that by using, let's say, logistic regression, and then add clever, where the offset is your initial estimator, the logit of your initial conditional probability estimator, and you add as clever covariate treatment over the estimated propensity score. Then you do a simple MLE, which is nothing else than running a univariate logistic regression. And then you have your update of your outcome regression. And then you are done, right? Then you take you evaluate it at AS1, and you take the empirical mean, and that is the TMLE. And that can then be analyzed like in the previous slide. And then all you're dealing with is that this remainder, right, this R1 at this Qn star minus Q0 and Gn minus G0, that has to be small and second order. And yeah, that means you need to have a good estimator. Here I'm just going to show you a little finite sample evaluation of what a TMLE update does. This is for a particular example we'll also be looking at. It's the integral density squared example. It's an example where now the remainder is actually of the form integral p minus p0 squared. So it's kind of an ugly remainder. It's always positive or always negative in this case. So that really can hurt your finite sample, normal approximation. And so it's an important problem. People have studied in the literature quite a bit. And we can do a TMLE update in the usual way. And here is a picture for a given data set where we plot how when epsilon is 0, you got back your initial estimator, right? And then along this path, this least favorable path, you moved from 0 to the actual MLE. And what happens then to your plugin estimator? And you see that it starts with this biased initial, and then it moves towards psi 0. And it keeps doing that till the likelihood is maximized along this path. You can actually think of this as if you would, for example, run a steepest descent algorithm. If you write down psi of the p tilde of the least favorable path in epsilon minus psi p0, and you square it, and you say, hey, I want to run a steepest descent algorithm. I want to minimize that in epsilon. You would actually be running the same algorithm because the canonical gradient of that squared will be the canonical gradient of psi times a constant, but the constant wouldn't matter except you need to know the direction. And so in the end, you are actually, during this TMLE, it is like literally running a steepest descent algorithm, minimizing the distance from your plugin estimator fluctuated towards psi 0, except at some point you don't know what the sign anymore is, and that's exactly the point where the likelihood is maximized, and that's where it stops. So you can only gain so much. But this is what it does in finite samples. Okay, so then in the world of TMLE, you still say, okay, I need a good initial estimator. And that's where we have proposed highly adaptive lasso as a very powerful estimator. In particular, we need one which gets this rate n to the quarter. Now, let's do a little review of what highly adaptive lasso is. So what we have is we can represent any multivariate real valued function, like a function on some kind of cube in higher dimensions. We can represent it as f of x as an integral of these basis functions. They're called splines, really, zero order splines. And then times the dfu, which is the increment of the function. So really what you're doing here, you write your function x as this infinite linear combination of indicator basis functions, which are defined as this phi ux, which is the indicator x bigger than u. I think of u as the not point, and it's a function in x. And so it's like if you have univariate x, then this will be like indicator x bigger than a cutoff. So it's a function which goes from 0 to 1 at the not point. But if x is two-dimensional, you also have indicator x1 bigger than u1 times indicator x2 bigger than u2. But you also have, because you're also integrating over null points along the edges, and that's where they become univariate indicators. So they become also indicator x1 bigger than u1 and separate indicator x2 bigger than u2. So you get all these one-way, two-way, three-way, up till d-way tensor products of these indicator-based functions. They're all in there, and your function can be exactly written like this infinite linear combination, where the coefficients are the actual increments of the function. And so what we do, we define the variation norm of the function as this integral of all these increments. In other words, the integral of the absolute value of the dfu. And this is increments in both the full dimension, but also in lower dimensions, because again, we also go over the edges of this higher dimensional cube, which are planes, lower dimensional planes, and even lines. So the conclusion is you can write any function, which is cadlag, right continuous left-hand limits, as an infinite linear combination of tensor products of these indicator, really spline basis functions, and where the L1 norm is actually the variation norm of the function, is how much it goes up and down. So that means with this representation, we can say, okay, many of our functional parameters like conditional densities, conditional hazards, conditional means, they all can be written. Often we do this, right? Like think about an density can be expressed in terms of a hazard, for example, and the hazard can be written as e to the power of some linear combination of basis functions. So that linear combination is now your function f. And similar with logistic regression, right? We take the logic of your probability and that becomes a freely modeled thing, which you write as beta x. So that becomes then again our linear combination. So you can parameterize many functional parameters, all of them really, in terms of this kind of freely varying cadlag function, which then is modeled with this big infinite linear combination of basis functions. So now you can define then a loss function, like the usual squared error or log likelihood, whatever it is. And we take the empirical mean of that loss and we optimize it, we minimize it over all these functions f. So all cadlag functions with a variation norm smaller than some constant. Now, since every function can be represented as a linear combination of these basis functions, it becomes really a lasso problem in the sense that you are minimizing an empirical mean over a vector beta, very high dimensional vector, because we are putting in lots of basis functions to really make the full approximation. And you just minimize this function over a beta vector under which the L1 norm is constrained, because that's the variation norm. And then you choose that L1 norm with cross-validation. So it's really like the regular GLM-net, right? That's in fact our function we often use to program these things for all kinds of functional parameters. And but it just happens to be with a lot of basis functions. Now, for example, we can therefore fit the nuisance parameters for the average limit effect problem, like the conditional probability of death as a function of the treatment and the covariance and the propensity score. We can all fit them with this highly adaptive lasso regression with n times 2 to the power d basis functions. And then choose the L1 norm with cross-validation. Now then you say, okay, that's nice, but how good is this estimator? Now, this estimator has actually a rate of convergence in loss-based dissimilarity, which is typically like L2 norms squares, or Kullback-Leitner dissimilarity, which again behaves like an L2 norm squared. The rate of convergence, if you take the square root of it, is n to the minus 1/3 times log n to the power d over 2. So in loss-based dissimilarity, it's always quadratic, so it becomes then n to the minus 2/3 times log n to the power d. So anyway, the rate of convergence is therefore n to the minus 1/3 up to log n vectors. So you see that the dimension has very little impact on the rate of convergence, and therefore your second order remainder, think about the AT, can be bounded by Cauchy-Schwarz and will actually start behaving like n to the minus 2/3, which is good, because if I blow it up with root n, it still goes to 0. So as a consequence, a TMLE that uses as initial estimator and HAL-MLE will be asymptotically efficient, only assuming that these true nuisance functions are cadlag and have finite variation. So that's what this example is. For the treatment-specific mean, we can now make the claim that if we use TMLE and use as initial estimator highly adaptive lasso for the propensity score and the outcome regression, and we just assume the positivity assumption, right, that at least we have support for this parameter, then all we need is that these outcome regressions and these propensity scores are cadlag functions, which is just, they can even have jumps. They just have to be right, continuous, left, and left, and they need to have finite variation norm. And then the estimator is asymptotically efficient. Okay, you might say that's nice, so we'll stop there. That's great, asymptotically, that's great, but let's not forget, in finite samples, the distance between the HAL estimator and this true function can still be large, because there's a constant in front of this rate, and this constant gets worse depending on the dimension. So this is still a very serious issue in finite samples. That remainder might really become dominating thing matters, and therefore your normal approximation might not be there for a finite sample. Therefore, we are interested in seeing, can we do better? Can we create, and that's where we talk about higher order TMLE. To make that remainder better, instead of second order, let's make it third order. Is that possible? So here's the idea, really the basic idea. So think about the TMLE, right? We have this Pn tilde 1p. That's the TMLE update, which takes as initial estimator p and then does this TMLE update along this least favorable path. And that TMLE update means you have this epsilon and that needs to be fitted with an MLE. So that's what I define there as Pn tilde 1p as this TMLE update. Plug that into psi. This is the plugin TMLE. This is the plugin TMLE when used as initial p. I call this now a parameter. So I'm actually going to think of it as a parameter in the initial. So this, I call it psi n1p. And then I say, so psi n1p0 is actually itself a target parameter. We call it the first order fluctuated target parameter. And when you think about the role of the initial, what do you want? You are going to plug in this initial in this mapping psi n1. So you want the initial to be a good plugin estimator of psi n1. So therefore, I say it makes sense to use as initial estimator p in the first order TMLE, the actual TMLE of this parameter. So in other words, this is a new parameter. Let's now construct a great plugin estimator for that. And we know TMLE has these properties. So we replace the initial estimator in the TMLE, the p, by a TMLE of this new parameter, this fluctuate parameter. And then you get this psi, which first does the TMLE, uses initial estimator, constructs the TMLE of this psi n1. That becomes then the initial estimator in the usual TMLE. And so you get this kind of sequential application of TMLEs, where the first you do a TMLE, that becomes the initial estimator for the next TMLE, and so on. So this can be generalized to kth order now, because the TMLE of psi n1 has its own initial estimator, and why you can say again, hey, let's tailor that towards its goal. And then you define a parameter psi n2p, and so on. So in this way, the initial estimator is tailored towards its goal to estimate psi n1p0 well. Okay, so is a natural idea. Let's say, okay, now I have targeted my initial estimate for TMLE for the purpose what it is. There is actually a problem, because to apply the TMLE to this parameter, I need to establish its pairwise differentiable. Now, it has dependence on p in two places. It depends on the initial here, right? In this least favorable path, there's the initial, and there's the epsilon, which is itself done maximized with epsilon n1p. So it also depends on p. Now, this one is very smooth. There's no problem there. But it's the MLE in P, which is in a way also smooth, because it's just like a maximum likelihood along a parametric model. However, because of the fact we use here the empirical, you cannot formally establish the pairwise differentiability, because you need then that some Rado-Nikodym derivative dPn over dP should exist. It shouldn't blow up. And that's why you don't get the pairwise differentiability. However, then we can say, oh, well, what is the idea of Pn when you maximize the likelihood, right? Pn is the empirical, which is nothing else than an NPMLE. Why not replace the NPMLE by our HAL-MLE, which is also an MLE, right? That's a model-based MLE. So now we're going to replace our MLE-step by maximizing the likelihood. Instead of over the empirical likelihood, we take the smoothed regularized likelihood, which replaces Pn by Pn tilde, the HAL-MLE. And we know, we have proven, right, if you undersmooth the HAL-MLE, so you choose the L1 and larger, you can actually show it starts acting like a regular NPMLE. It solves all these core equations and even uniformly over a large class. And also it should be noted, for components of the initial estimator that are fitted with the empirical measure, we can set the Pn tilde component to the empirical measure as well. So we don't need any smoothing for certain components which already are estimated empirically. It's only for the components where we will apply smoothing, such as machine learning. Once we have done this, with this little twist, we have now that our psi fluctuated target parameter is now pairwise differentiable. It has now a canonical range, I call it D2, and it has a corresponding exact remainder. And so now we're ready. Now we say, okay, now I can construct a least favorable path through P, which targets this psi n1, this fluctuated target parameter. And I can do the TMLE, so I do the little MLE, except I do it regularized with respect to this HAL-MLE, so a little smooth one. And I construct this I make that the initial estimator for the first order TMLE. And I plug it in. And this is called the second order TMLE. So that's the overall idea. And And I think this is a moment for a few questions, if there are any, before I dive into why this is such a good idea and why it really helps to reduce the bias.
Thanks, Mark. So there's a question in the Q&A that's been answered by ZE, but maybe it's of broader interest. So what type of functions fail to have finite sectional variation in moderate high dimensions?
Yeah, I mean, to start with, you need to realize that any kind of continuous function, is essentially included in the class of all cadlag functions with finite sectional variation, except if this continuous function gets completely crazy, right? When it goes up and down forever. So that's a huge class already. On top of that, it can have jumps, right? Cadlag functions are allowed, just like CDFs, cumulative distribution, can have jumps. So it can have, except the jumps have to be along what I think of as rectangular discontinuity lines. So in other words, I cannot have like some kind of circle jumping up out of my function. But if the discontinuity happens along lines, the axis, then it works, right? So there's the type of discontinuities are controlled, and that's the kind of things you start where it would not be cadlag and you run in problems. But the variation norm is really, that is bounded, is kind of what you expect in the real world, right? You don't expect necessarily, maybe some exceptions, that there are functions which just keeps going on and on and on. Especially if we focus on functions on compact support. And I should say that I always do that. We always work on functions on compact support because, once you get to the whole line, it's really getting very difficult. So yes.
Yeah, that makes sense. Thanks. Another question that's popped up in the chat is about the inputs of the algorithms. In particular, one is whether you have to specify the canonical gradient or whether it's something that can be obtained numerically.
Yeah, that's a very good question. And actually in the tech report, which is on the front page, which is really what this is based on, and we just made a tech report yesterday, there's whole sections we have written about exactly that, how we can do the computation with purely numerical algorithms of these canonical gradients, because you can represent these canonical gradients as also linear combinations of essentially spline basis functions, except transformed through the score operator. So, and then it becomes nothing else than some kind of regression problem. And in fact, it's all about Cholesky decomposition and inversion of a symmetric matrix, or regression. There are two ways to do it. So in the end, all of this can be learned, these canonical gradients can be learned with pure computational regression or computational numerical routines, such as computing a Cholesky decomposition. So this can be completely brought into the world where you don't even have to know about Hilbert spaces and projections and all that, even though that's what we have been doing in the past. So I really see that in the future, we are moving exactly towards a world where we start bringing in the power of the computer to just compute these approximations. And they also have advantages, by the way. Work with ZE Wing, we're seeing them, is that by representing the efficient Hilbert curve as a nice closed form object, just a linear combination of basis functions, you get real advantages because you can evaluate even at observations outside your, where you actually had observations. So you had like at new observations. And so it really, and it also has some stabilization effect. So I really think, but yeah, that's an excellent question. So.
Thank you. Yep. Yeah, thanks. I'll let you continue with your talk. Thanks.
Okay. Yeah. So so to understand more theoretically. So yeah. So this sounds fun, right? It's a good idea to make this initial estimate tailored for its goal. So just make it in TMLE itself, but then TMLE of what it's actually used for. However, let's try. We need some theory, right? That this is truly a good idea. Now, the first theory is it's actually, you can define what I call the exact total remainder. So in other words, write down the first order TMLE which is an update of an initial P, right? And we want to understand how to choose P. Why it's such a good idea to make that the second order TMLE update. So write this minus psi P0 and subtract the empirical process at the first order canonical gradient using the true P0. So this is like a perfect, that's the total remainder. The only twist is that it's Pn tilde and not Pn. But that's where the undersmoothing happens, and then this starts behaving like Pn minus P0. So this is really what you care about. You want that to be small. That's the remainder, right? After that, you just have an empirical process, an empirical mean. this term actually equals the remainder R1, right? We already had the exact remainder, and then this additional empirical process term. So that's the remainder. You can think of this as a function in the initial P. By changing the initial for the first order TMLE, I might make this smaller or bigger. And we like to choose an initial which makes this as small as possible. Then comes that when you work out, you can actually show that this exact total remainder can be written as exactly this fluctuated target parameter, psi n1p minus psi n1p0 plus something which doesn't depend on p. This is a perfect remainder using as initial p0 for the TMLE relative to p0. Has nothing to do with the initial. So what you see, when you want to minimize the exact total remainder, it's all about this fluctuated target parameter approximating its target estimate, psi n1p0. So now you see why it's a good idea to use there to make this as close as possible to that. So essentially choose P to optimize this, to minimize this difference. And that's precisely what TMLE does. And so formally, what happens, if I now replace here psi n1p by a TMLE of this, then this whole thing, this here, starts behaving like a TMLE. So that means it behaves like we know with TMLEs, right? We have this key identity. We then know that the psi n1 of its TMLE minus psi n1p0 behaves like this empirical process of the second order efficient impulse function plus an exact new remainder, the remainder for that parameter, which actually happens to be third order. So the exact total remainder becomes, then I can plug it in, right, for this, because remember, here was the formula. So I can now plug this in, and that becomes this, and then I still have that perfect remainder, which had just only p0 in it. So now you have replaced this remainder for a regular initial p by using for the initial in the first order TMLE, this second order TMLE update. We actually replaced it by adding an additional empirical process term plus a perfect remainder here. And then here comes this new remainder, which is actually going to be third order. So that's what you now have formally achieved. And also, to summarize.
Sorry to interrupt, you have around 10 minutes left.
Yeah, that's fine, that's great. So to summarize, when you compute, here's the first order TMLE minus truth, it can be written as this empirical process with the first order influence plus an exact total remainder. The exact total remainder equals exactly this new parameter psi n1p minus psi n1p0 plus a perfect remainder. And to optimize the exact total remainder, you therefore want to make this a TMLE. And in fact, you can show, similar with a first order TMLE, that if you would run an Oracle steepest descent algorithm optimizing this guy, even though you don't know it because you don't know P0, right? But suppose you do know P0, and you literally say, oh, this is what I want to optimize in P. You would run a steepest descent algorithm by every time moving along a path with maximal change of this, right, along the steepest descent. You would literally be running exactly the second order TMLE algorithm along this least favorable path, making local moves every time, which we call a universal least favorable path. Except if you know this guy, you would even keep going till the end. With the second order TMLE, at the moment you have maximized your likelihood, you stop. Because the canonical gradient of this guy is a constant times the canonical gradient of this guy. And the constant becomes, the moment the likelihood is maximized, that constant, you don't know which direction to go anymore. So that's why that's the moment where you then stop. So, but up till that point, you literally are optimizing the exact total remainder for your given sample. That's what this picture shows. This is, again, just a simulated data set. We look at that exact total remainder along this path, right? When we, at epsilon is 0, this is where we have an initial. The first order TMLE gets some bias reduction, right? Moving us to the bias, the remainder smaller, yes. But then here comes, for epsilon is 0, for that second order TMLE update, which again, a path through the initial estimate. Here we are still getting the first order TMLE. As epsilon moves, so the initial starts changing, we are getting bias reduction. So this remainder gets smaller and smaller till the point where, you know, we don't really know what to do anymore. And that's where you then are stuck. And that's how far you got. But you can see massive bias reductions happening in this given sample for this given data set just by changing that initial estimator through this, along this least favorable path. And here's another example where actually the first order doesn't do anything. It's just terrible because it's because of a certain setting. And the second order, by just changing the initial estimator, we still get huge bias reduction and therefore get this exact remainder reduced a lot. We also get an exact expansion for the second order TMLE, which essentially we already derived, but there's a little trick we use, which links the remainder at P0 to the remainder at P n tilde. And then we get a beautiful exact expansion, and that's this one here, which says that the second order TMLE minus truth, so the plug-in estimator minus truth, is an empirical process of the first order efficient function, plus an empirical process of the second order, in other words, this efficient function of that psi n1, plus perfect remainders, right? Because this is just the TMLE update when you use this initial P0. So that's really negligible. And then finally, here comes the remainder, which is not an empirical mean anymore, empirical process. And that's this difference of the Rn2, which is the exact remainder for this new parameter psi n1. And this is third order. And in fact, you can link it to the first order remainder by just writing it as the first order remainder of this sequentially updated initial relative to P n tilde. So this is an exact expansion, which involves both an initial estimator and the P n tilde used for the HAL-MLE. And it defines this exact expansion. And there's also a way to target P n tilde. Instead of undersmoothing, you can target it to make this more directly behave like an empirical mean, so that you get rid of the bias due to the smoothing of P n tilde. So that's what this says. By undersmoothing the HAL-MLE, these P n tilde means, the means under P n tilde starts behaving like the empirical means. And so this becomes more and more negligible. And therefore our exact expansion starts now all being about this, which is of course perfect because this is now an empirical mean of mean zero independent random variables. It just has an additional influence curve component, which is this one, which actually goes to zero. So statistical inference can then be based not just on the first order influence function, but also on the second order, so that you pick up the second order term in the remainder in a way you pick it up in our normal approximation, and we're only ignoring a third order remainder. So that's the advantage that you get from it. We can generalize this to kth order TMLE very naturally, right? And then you get that this sequential. You compute an initial estimator, you make it, you compute the TMLE, and then that becomes the initial estimate, the next TMLE, the next, and finally you're back to the first order TMLE, which uses now this highly targeted initial estimator. And then you get as a result that plug-in TMLE minus psi p0 is again a sum from J1 to K of pure empirical processes, little regularized through P n tilde, plus perfect remainders, and all you're left with beyond this kind of nice empirical mean terms is this Rn k plus 1, which is now a k plus 1 order difference. So it's like an integral of p minus p0 to the power k plus 1. And again, you can relate it to the first order remainder because it happens to be, it's the first order remainder where you keep just targeting and targeting and targeting it sequentially. And every time when you target, you get a reduction in order. You get the first, second order becomes third, and the third becomes fourth, and so on. Okay, so I want to end the last few minutes with some simulations. These are simulations for the treatment-specific mean. And here you see for the bias of the first order TMLE, bias of the second order TMLE, we make the propensity score n to the quarter consistent, but Qn0, the outcome regression, is inconsistent. So in this case, you would expect that the first order TMLE should have a skill bias, root n skill bias that actually increases, so it's not even asymptotically linear. The second order TMLE should have a root n bias which should become constant. So it's not perfect asymptotically, but actually what you see in finite samples is that the bias is dramatically reduced by the second order TMLE, right? You go from a 0.72 relative to a standard error, so that means convoluted intervals are horrible now. But for the second order TMLE, the bias is still negligible relative to the standard error, and therefore you get great coverage and all that, even in a situation where it's not even theoretically, there's still too much inconsistency. Because our third order term will be exactly n to the minus half now, because we will get a gn0 minus g0 squared. So for the second order TMLE, we at least get to that level in this case. But even in finite samples, it actually seems to just work. Now here's a situation where both are n to the quarter consistent. That means the first order TMLE is just not asymptotically linear. It has too much, it still has a root n level bias. The second order TMLE should be fine. And so again, you see the bias is indeed staying constant once we scale it at root n. for the first order, but for the second order TMLE, the bias is you know, smaller by a factor a lot, right? Factor 10 and so on. So you get big gains. Similar for the integral of the density squared, which is a particular interesting problem where the remainders are non-forgiving. And so that's why I say here, the second order TMLE will replace this tough second order remainder, which is always positive and therefore hurts. Not only by a third order remainder, but it will also be a remainder with all that cancellation going on, like we have seen with the ATE problem, right? With the double robust, there's a lot of cancellation happening in that remainder. It's not like a square. So the squares will be gone. And so that's the benefit. Now here's simulations done for this integral density squared, and where you see the bias. And here we increase the bias in our simulations. And you see here the second order TMLE and then the undersmoothed, because we undersmoothed the HAL-MLE. And you see that as the bias that we get, you know, small bias with the second order TMLE, while the first order TMLE gets worse and worse and worse. And here's the ratio of bias versus standard error. If the bias over the standard error starts converging to 1 and so on, you have terrible coverage. So you see the first order TMLE suffering, but then the second order TMLE pushes it towards, you know, 0 essentially. So you get good coverage. And here are then some numbers where you see, for example, here, you know, 1.37, and then here you get a whole order a bit better. And similar here, we go from 10 to the -3 to a 10 to the -5 bias, which is really a massive reduction in this problem. Okay, so I end with some concluding remarks. So the cave order TMLE allows a linear expansion with a remainder that is in K+1 order difference. It involves these empirical P n tilde minus P0 of functions. So it's a nice, it's an almost empirical means with a little bias due to the HAL-MLE, but that's controlled by either undersmoothing or targeting. Dramatic reductions in bias due to second order TMLE are observed in simulations. It not only weakens the assumptions on the initial estimate in the TMLE for asymptotic coefficient, but has clear finite sample impact on bias and improves coverage of confidence intervals. In particular, appealing an estimation problem in which second order remainder behaves like squares, which we also have in causal inference. Higher order TMLE also opens up a road for inference in problems with the first order efficient inverse curve disappears. So there are these kind of problems, and now we can look at that higher order expansion and start using that for inference. Algebra and pure computational methods are developed for computing these higher order efficient inverse curves, which are very doable. It's a constructive procedure. Once you have the first order, that gets you the second order. Once you have the second order, it gets you the third order, and so on. And it all can be done through numerical algebra routines. And I end here. And thank you very much for your attention.
Fantastic. Thanks for the very interesting talk, Mark. We're now switching over to the discussion. We will have Alex Luedtke present some slides. After that, Mark will be able to respond. So now I'm switching over to Alex. Alex, whenever you're ready.
I stop share, right?
Yeah, and Mark, you should stop sharing. Yeah. Thanks.
All right. So thank you, and thank you to the organizers for having me. And also to Mark for some helpful discussions over the last week or so. So I'll start my discussion. I'm just going to give a high-level overview, just a recap of the approach that Mark has described and what it's aiming to accomplish. So I use relatively similar notation, but I simplified in a few places. So here, M is a statistical model, so just a collection of possible distributions that should contain the truth. And psi is a parameter, so it's mapping from a distribution to just a real number. And so a TMLE we can think of here as a data-dependent mapping, and all it does is it takes as input for the purpose of what we care about here is an algorithm that takes as input an initial fit of the distribution P0 of the truth. And then it returns an estimate. So psi n of p hat, where p hat is the initial fit, is just an estimate of psi of p0. Okay, and expressing this estimator in this form is very important for the development for the developments that Mark makes as he progresses towards a second and higher order TMLE. So perhaps this isn't too surprising, but if we did happen to have access to the true data generating distribution, if we had sort of oracle access to the true P0, then a very good estimator to use would be just to sort of run the usual TMLE and plug in the truth P naught in that case. Of course, this is unachievable. We don't have access to P naught, but just sort of for the sake of a thought experiment here, if we did have access to P naught, how would this estimator behave? Well, in this case, the TMLE minus the truth would have this optimal first order behavior plus this very small remainder term here, thanks to the fact that we really have access to the truth here. Okay, so this sort of orange term is really behaving as well as we can possibly hope to behave based on this estimator. Okay, and then also, of course, we don't have access to P naught. So if we plug in any other initial fit P hat, we can always relate the deviation between our TMLE evaluated at P hat to the truth, from the truth rather, by just adding and subtracting this sort of oracle estimator here. And what we end up with is this leading term is sort of this sort of perfect term, the best we could possibly hope for. And the second term here is like a deviation between our TMLE, our estimator, this algorithm if we feed it P hat, versus this algorithm, this estimator, if we feed it P naught. Okay. And so what the second order TMLE aims to do here is it aims to ensure that P hat is such that this term up here is small. That is to say, this psi n of P hat is a good estimator of psi n of P naught. And now we need to be a little bit careful here because note that as the n perhaps suggests, psi n is a data dependent parameter. So it actually depends on the data. But we can still think of psi n as just a mapping that takes as input some distribution in our model and returns a real number. Okay, so what Mark does when he develops this higher order TMLE is he studies this parameter psi n, and then he tries to develop an estimator for psi n of P naught. Okay, so maybe just a caveat, because this turns out to be important for a discussion point that sort of I'll conclude with. So the usual TMLE, if we think of this psi n of P hat algorithm, is a plug-in estimator of a maximum likelihood estimator. And so what we do is we plug in, so our final TMLE is just psi of Pn star. Pn star is some estimate of P naught. And the way we get to Pn star is we just fit a maximum likelihood estimator within a particular model. And this particular model is carefully chosen. I won't worry about, for now, about how it's chosen. But this model, I guess the key point is it's really centered about P hat. So we could think of it as a little perturbation of our initial distribution. Okay, so this depends on P hat. And it's in this way that we could think of this, the TMLE as an algorithm mapping from P hat to an estimate, or taking as input P hat and returning an estimate rather. You know, there's a problem that arises if we try to study this TMLE as I described on the last slide. And the problem is really, well, it turns out that this psi n parameter isn't pathwise differentiable. It's not sufficiently smooth for us to be able to really construct a good estimator. So what Mark does when he's sort of pursuing this higher order approach is he says, okay, well, rather than fitting this Pn star via maximum likelihood, what I can do instead is I can find some smooth surrogate for the empirical distribution. So on a later slide, I'll make it clear sort of what he's asking of that smooth surrogate, sort of what requirements it must have. But we can often think of it as like a density estimator if everything's continuous. And then Pn star here will define as a Kullback-Leibler projection of Pn tilde onto this exact same model M of P hat that I described on the last slide. Okay, and then the TMLE is defined in exactly the same way, where I just take Pn star and I plug it into psi. And it turns out that under conditions, essentially that Pn tilde is smooth enough, the resulting parameter psi n is in fact pathwise differentiable. And so this provides Mark a means to sort of iteratively go through and say, okay, well, if you give me a pathwise differentiable parameter, even if it depends on the data, I do have an approach for constructing an estimator of it. So I'll just go ahead and do that. And I'm going to try to estimate now psi n of P naught. Okay, so that's sort of the logic that underlies the algorithm that he described. And so on my last two slides, I just want to make sort of an observation. So I guess this is an interesting fact, which is that if we look at the KL projection on this last slide, and if it just so happens that P hat is exactly equal to Pn tilde, so in this case, again, M of P hat is just some model that involves perturbations of P hat, and so it certainly includes P hat. So if I take the KL projection of Pn tilde onto the model M of Pn tilde, then the KL projection will just be equal to Pn tilde itself. So all that means here is that the TMLE when we take the initial just to be equal to p n tilde, just returns p n tilde. It doesn't do anything. It just takes p n tilde, plugs it into the parameter. Okay. It turns out if you iterate this logic, you can see that, in fact, the kth order TMLE, if you use p n tilde as your initial, is still just going to return p n tilde. No matter how large you make k, no matter how many iterative steps you take in this procedure, you're always just going to return psi of p n tilde. Okay, so in some sense, this shows how critical of a role that p n tilde plays here. You really need, at least if the initial is p n tilde, you really need that psi of p n tilde is a good estimator. Okay, and it turns out under certain conditions, smoothness conditions that involve this bounded uniform sectional variation norm, also known as the Hardy-Krauss norm in the literature, in case that's helpful for folks to make a connection there. You really do need sort of certain smoothness properties in order for this higher order TMLE to return a nice estimator in the case that you use p n tilde as the initial. Okay, and so that said, sort of in spite of the fact that from an algorithmic perspective, when you use p n tilde as your initial, the kth order TMLE is just going to return psi of p n tilde. Nonetheless, the analysis that Mark did of this higher order TMLE still provides a very interesting and sort of novel expansion here, where we can come up with a new way of studying the simple plugin estimator psi of p n tilde, where he comes up with this nice expansion where we have so some term representing optimal first order behavior here. We have a term that is sort of expressing how important of a role p n tilde plays. We really need that p n tilde for certain distributions, its mean looks a lot like the empirical mean. Then we have some negligible terms that really won't come into play. And then we have this very interesting orange term, these second and higher order terms here, that look like an empirical mean minus a true mean of certain functions. I think Mark, these sort of play the role kind of higher order gradients here. And these functions actually do depend, so they're random through p n tilde and p naught. So we need to be a bit careful. We can't just necessarily interpret these as converging to sort of some nice normal or being faster than Bourdin, depending. We need to be very careful in sort of seeing how p n tilde impacts these gradients. And Mark has studied this somewhat in his paper. But in any case, this is very interesting because it potentially provides a means both to study this plugin parameter psi of p n tilde, and also potentially to do higher order bias corrections. So I think it's sort of interesting, and I'll be interested in future work to see whether anyone sort of is able to make further progress on this. So I'll stop there.
Thanks for the great discussion, Alex. Mark, do you want to respond quickly?
Sure, yeah. Thanks a lot, Alex. That was wonderful and very clear. Yeah, so one of the points, the main point Alex is making is that when you use as initial, in other words, we have this general higher order TMLE, and it has as ingredients an initial estimator Pn0, and it has another ingredient Pn tilde, which is the HAL-MLE. And that gives us an exact expansion. And that exact expansion tells us in particular what we need about Pn tilde, about the HAL-MLE. Namely, that the empirical mean of the mean under the HAL-MLE minus the empirical mean of these higher order influence functions is negligible. That's the role Pn tilde needs to play. Now, that itself allows us to now say, okay, we have Pn0 and we have this HAL-MLE Pn tilde, and we have room, right? One is indeed, you can say, why not just make sure these the HAL-MLE is undersmoothed appropriately or is targeted appropriately so that it solves these, that it acts like an empirical mean on these higher order influence functions. And once you have achieved that, then just use the HAL-MLE. In other words, just use the plugin of that HAL-MLE, which is now undersmoothed appropriately or targeted appropriately to solve these higher order influence functions. That is a great estimator. There's no doubt about it. And then, you know, I'm a fan of undersmoothed HAL-MLE. It's really, it is the analog of MLE for parametric models, except for infinite dimensional models. And it's a plugin, and it automatically, without, if you undersmooth, you don't even know what you're targeting. But for all these target parameters, you can uniformly prove it will be asymptotically efficient. And so you might say, why are we not just, and indeed, like Alex was saying, this work allowed me to analyze this HAL-MLE and this undersmooth HAL-MLE in this particular way, giving us insight that it is in many ways a higher order optimal estimator. As you undersmooth, you start knocking out all these terms and you start essentially behaving like this big empirical mean of higher order influence function. And that also allows us to do inference for this type of plugin HAL-MLE, like again, Alex was mentioning, by incorporating these additional terms. I would even argue that even that bias term, which is Pn tilde minus Pn, applied, which is supposed to be negligible if you undersmooth, you could still say, yeah, but it's still there. Why not bootstrap this whole expansion, right? Because you can bootstrap. That's the beauty. We have shown that nonparametric bootstrap works beautifully for HAL. So we can probably even bootstrap that bias term and just make that part of the inference. And so that itself means we have a contribution towards this kind of plugin HAL-MLE for both inference, also for how you should be undersmoothing, because we can now track if we have undersmoothed enough, because we know what the goal is, namely to solve these higher order influence functions. So that itself is an important contribution to the whole plugin HAL-MLE world. Are we then saying, why even bother doing then still this kind of higher order TMLE? Why not just work with this, cleverly undersmoothed or targeted plugin HAL-MLE? I would argue yes, because this gets now to the comparison of a plugin HAL-MLE versus a TMLE. And TMLE has the benefit I can choose as initial estimator something highly adaptive, because if you use HAL, that's very non-parametric. But depending on the dimension and depending on the underlying smoothness, maybe we need higher order splines, which we also have. Maybe we need fewer basis functions. We don't need the higher weight basis functions, and not just let the algorithm figure it out. Let's help it, right? So in other words, start building a superlearner with cross-validation to choose between all these different adaptive algorithms. In this way, we can construct an initial estimator which will do significantly better in finite samples than HAL for approximating P0. And then the targeting pushes it towards the HAL-MLE through these MLE steps, but it still preserves a lot of its initial adaptive nature. And the HAL-MLE plays now purely the role of still being able to maximize a likelihood, right? Because it will have a significantly larger likelihood than any kind of initial estimator, and therefore gets these bias reductions. And in particular, it can incorporate knowledge about nuisance parameters, orthogonal nuisance parameters, to really get maximal bias reduction. So in this way, it's a contribution to the TMLE world, because that's the contribution of TMLE, that it allows you to do that targeting towards very specific target parameters. And we also have shown in the stack report that you can actually really even target the HAL-MLE in such a way that the MLEs are identical to what they would be under the empirical. So now it's truly nothing else than a regular TMLE with just extra targeting. And so you're completely in the world of regular TMLE, but with all that extra targeting. And so that's where it is a real contribution to the TMLE world. Having said that, I think both estimators are of great interest. And I'm a fan of both, let me put it that way. I will stop there.
All right, fantastic. Thanks, Mark. I think, we're slowly running out of time. So let me wrap up. So first, thank you, Mark, for a very interesting talk. Thank you, Zeyi, for helping out in Q&A. And thank you, Alex, for the very interesting discussion. Next time, we're going to have Stephen Bates from UC Berkeley, who will talk about causal inference in genetic trial studies. We're looking forward to that. Until then, we hope you all stay safe and hope to see you next time. Thank you all for coming and hope you have a good week. Thank you.
Thank you.